So now let's look at how electrons are distributed inside of a semiconductor in terms of their energy. So statistical mechanics is the branch of physics that helps us solve this problem. The book gives a little more detail, but what we need to know here is that the electrons are distributed according to energy by what's known as the Fermi-Dirac function. So the Fermi-Dirac function is a probability function, and it's given by 1 plus exponential, 1 over 1 plus exponential to the energy minus EF over kBT. So kB is the Boltzmann constant. In joules, its value is 10 to the minus 23 joules, and in joules per Kelvin, and in electron volts, it's about 8 times 10 to the minus 5 electron volts per Kelvin. So this function, if we plot it versus energy here, goes between 1 and 0, and it sort of looks like a step function that's been smeared out a little bit. So the transition width, sorry, my pencil decided not to work. Is of order kBT wide. So if you go to 0 Kelvin, this does reduce back to a step function. So what this says is basically up to a certain energy, the quantum states are all full of electrons, and then above a certain energy, they're all empty of electrons, and that is strictly true at 0 Kelvin. So this energy that we're talking about, the EF, is the so-called Fermi energy. Okay, so what we could do is then let's take the last two topics and put them together. So this is not OK, this is 0K, and let's say now we have a density of states function in the conduction band, and let's imagine here, so this is our energy, and let's imagine our Fermi energy is somewhere below the band edge, and we're at some reasonable temperature, like 300 Kelvin. Sorry, this is misbehaving a little bit. So here's our Fermi-Dirac function here, and because it falls off very quickly, exponentially quickly, there's just this little exponential tail of population of the conduction band. So we're going to blow this up and look at it more closely over here. So now this is our energy. Our 0 here is EC. Our square root density of states goes like that, and our Fermi-Dirac function comes in exponentially decaying like this. So if we multiply these two things together, we get a shape that looks something like this little area that I'm filling in here. So this little shape is actually the distribution of the number of electrons per unit volume per infinitesimal energy range. So really what this says is that right at the band edge there's not many electrons because there's not many states. It rises to a maximum probability of where most of the electrons will be in terms of energy, and then it tails off to 0 because of that exponentially decaying probability density from the Fermi-Dirac function. So the Fermi-Dirac function is not quite ideal, and especially in cases where the Fermi energy is more than a few kBt away from the energies you want to talk about. So as long as EF, as long as EC minus EF is greater than about 2.5 or 3 kBt, we can make an important approximation, and that is called the Boltzmann approximation. Oops. We can approximate that F of E is approximately equal to exponential to the minus E minus EF over kBt. And this is basically saying that in the denominator this 1 is irrelevant and the exponential function dominates here. So this is the so-called Boltzmann approximation, which is very useful to use, and we can use it for most of the time in semiconductors, except at very high doping densities usually. So let's just note a few more properties of the Fermi-Dirac function. Mathematically, since it varies from 1 to 0, it turns out that the 50% probability occurs right at the Fermi energy. Oops. So that's one. Excuse me. That's something I'll refer to ahead in a little bit when we're talking about the intrinsic carrier density. It tells you, roughly speaking, where the Fermi energy is in an intrinsic semiconductor, and the answer is basically halfway in the band gap. Another important thing, the Fermi of energy, the Fermi-Dirac function as a function of energy is giving you the probability of states being occupied with electrons. And since a hole is the absence of an electron, we can say that 1 minus F of E should give us the probability of holes occupying. And if we work out the math, if we do 1 minus 1 over 1 plus exp to the E minus EF you can do the manipulation here and find out that the sign in the numerator basically changes. And if you do the Boltzmann approximation, it gets even easier to see. So for holes, the distribution function, the Boltzmann approximated distribution function, is going to be kind of the same thing, but we're going to put EF minus E over kBt. And so this tells you, if energy is going this way, and our Fermi-Dirac function for electrons would go like this, then for holes it would look the opposite, and the hole population will be decreasing as you go down in energy further away from the valence band edge. So again, you'll get a distribution of holes in the valence band with a similar energy distribution, very few near the band edge, rising to a maximum, and then exponentially decaying. The probability of getting these holes at energies far away from the band edge is very small. Okay, so now we've got a continuous function called the density of states. We've got a continuous function called the Fermi-Dirac distribution, or its approximation, the Boltzmann distribution, which can describe which states are full or empty of electrons and holes. Now we're going to go on to actually figure out the numbers of electrons and holes occupying the bands in a semiconductor. That's the next chapter in the book, so we'll start a new round of videos in the next module.